Synchronize. 3, 2, 1. Wait, you remember this? We didn't take this audio yet. Alright. Hello. Hey guys, are you wondering why radical bromination is so damn picky, but radical chlorination is not that picky? Also, what the heck is Hammond's postulate? Hammond who? Well, we're going to figure all that out today in this video. So, first off, do you know what a radical is? I hope you do. The radical is basically just that black dot. It's a single electron that's not paired up, so it's super, super unstable. And what radicals do is that they bounce around through different molecules like this one, or other molecules in your body, and then they can cause new radicals to form, and then that causes DNA damage, which can eventually lead to cancer. So yeah, kind of sucks. But let's turn it back to a happier note. A radical like this one can actually be stopped from bouncing around and causing DNA damage if you just pair it up with another radical. If they crash in together, then the two electrons pair up and stabilize. Kind of like this.
Want some coffee?
Sure, thanks. So in order to understand this video and understand the selectivity between the two reactions and Hammond's postulate, you have to be super, super familiar with, well, the two reactions themselves and how they work. So first off, we're going to quickly review the two reactions, bromination and chlorination, what's the point of them, and also the mechanism behind it. And then we're going to create an energy diagram based on the mechanism. And then you'll really clearly see why Hammond's postulate is actually really helpful. A lot of professors in classes, they don't quite explain it enough, but I'm going to do that today. And this might end up being a two-part video because there's a lot that I have to talk through. So first off, bromination, what's the point? Chlorination, what's the point? It's not to add a Br on, actually. Well, it is, but a lot of people forget that it's to actually pull off the missing hydrogen that I haven't drawn yet, pull off that hydrogen and substitute on a Br, okay? That's going to be very important, especially if you have to do the mechanism. All right, so yeah, that's the point of the two reactions. But bromination is way more useful, or I'm sure your professor has told you, because it gives you predominantly just one product versus chlorination, which gives you a mixture. And that's bad because if you're trying to create Advil, ibuprofen, or Tylenol because you have a headache, you don't want to create a second product that causes diarrhea. That's a little bit not too convenient. So first off, I need you guys to show me that you know the mechanism behind these two reactions. So review your notes, draw them out, and we'll come back and regroup in a few seconds. All right, hit pause, and I'll see you in a few seconds. Do it. All right, did you guys get this? Yes, you guys are probably smart, so I assume you guys got this. But did you? Anyways, well, hopefully you got that. Real quickly, I should have explained this earlier, but I added this in. Sometimes my students get confused about the 99 and the 1. So basically, you have not just one molecule in your beaker reacting. You actually have like tons and tons, billions. But for simplicity, yeah, beaker. Anyways, for simplicity's sake, we're just going to pretend like there's only 100 molecules reacting in our beaker, and 99 of them became this product. 1 became this product, and 37 became that product, and 63 became that product. Okay, so that's how the percentages come in. What you should have gotten was this for your mechanism. I didn't draw in the arrows, and I'll do them right now with you guys. But I wanted to point out a few things. First, this part. When professors teach this reaction, they don't quite include this part in here. It's not actually 0.01%, but I just wanted to show you guys that it's a really, really tiny amount of Br, and Cl that breaks up into the radical forms. Why? Well, it's because it's super unstable. Why would a happy Br couple and a Cl couple break up to become radicals, right? They need heat, HV, heat or light. HB basically means light as well. But you should see these three conditions because you need them to destabilize your halogens in order to motivate them to break apart. So yeah, that. And then I don't think your professors will teach you this, 0 to 2 and 1 to 1, 0 to 2, 1 to 1. What that means is, can you actually guess? What am I referring to by 0 and 2 and 1 and 1? Well, I'm referring to radicals. In initiation, you're always starting with 0 radicals and producing 2 radicals. Propagation, you start off with 1 radical, you end up with 1 radical. And there's actually 2 propagation steps, as you can see. Okay? What I also wanted you to see is that the mechanisms are basically identical for each. So why is it that this is still so not selective and that's so picky, right? It's weird. Well, let's do the mechanism first and then we'll go into that. So first, you want to break up your bond like this because there's 2 electrons in that bond. Okay, so that breaks up, you get your radicals. Then this Br is going to come in with its radical. Oh yeah, one of my students from back in 2014, not a train wrecker, she thought of, she's funny, she thought of radicals as home wreckers. Don't be a home wrecker. But basically, happy couple, they broke up, they both became home wreckers. This one is now here. This comes in, breaks up this stable bond, and there's two electrons in that bond there. One electron is here, one is here. This electron comes over to form the bond. They kiss. This electron stays there, so you just draw an arrow like that, and then you get this. And now this molecule now became your new home wrecker, or your radical. So that, we're going to transfer that down here. Forget about our HBr, it's not really necessary. I'll talk about this stuff later, the endothermic, exothermic. But that comes down here, and then this radical is going to come here, break up this happy Br-Br couple. This is going to go here, that's going to go there. And then this 1 electron meets up, kiss, 1 electron goes over here, create the radical, and here you go. This pathway up here and up here is how you get to your tertiary product, and that's why I have 2 for each propagation step. Propagation 1, I have 2 pathways. Propagation 2, I have 2 pathways as well. The top one is for the formation of the tertiary product. The bottom one is for the formation that leads to the primary product. All right, so similarly, over here, this home wrecker, Br radical, comes in and then wants to make a bond with a hydrogen. So 1 electron in this carbon-hydrogen bond. This electron versus this electron. This one goes, meets up, kiss, make a bond. This electron, where does it go? Just stays there. But we still have to draw an arrow for that. So we draw that fishhook arrow because we're dealing with only 1 electron movement, so we're using the fishhook arrows instead of the double head arrows that we do for resonance. Okay, so there you go. That creates this radical here. We transfer this radical down here, just like before, ignore the HBr. Doesn't really do much of a job later on. So here, this radical comes in, breaks up, kiss, last electron goes over here, boom, becomes a radical. Now this radical can go back into propagation 1, where it can then react with another copy of the original alkane and go through propagation 1 again to give us our tertiary or primary product again. But as we can see, it mainly produces the tertiary product, which we're still trying to figure out why. Okay, so transferring over here, the mechanism is going to be exactly the same, so I'm just going to zoom right through this one. Okay, same thing, Cl, break up, home wreckers, radicals come in, home wreck, in you go. Bond meets up, kiss, electron forms radical, transfer that radical down. This radical is now going to be the home wrecker. Kiss the Cl, make a bond. Bond goes here, electron goes there, you get your radical. Boom, tertiary product. Same thing here, Cl comes in, kiss. You know the drill, bring it down. This one reacts over here, meets up, kiss, becomes a radical. All right, and then just like before, it regenerates. And because it goes back, oh wait, that's not what I was trying to say. What I was trying to say is that, as you can see, the radical is unstable, and it can react with another molecule that's not a radical to stabilize itself. But then, that molecule is screwed, and it becomes a radical. And that's why radicals can jump around your body, like I said earlier, and cause a whole bunch of DNA and cell damage. So, eat your greens, and don't eat so much fried foods. But yeah, fried foods are awesome, so just eat your greens and fruits. Okay, here we go. Next, what do you have to do? Well, now you know your reaction pretty well, and So what we have to do is actually transfer this mechanism into an energy diagram. So this way you can better see why Hammond's postulate is actually really useful. I know, sounds like it's going to be a pain, but it's actually not that bad. The energy diagram I'm talking about is like that thing, axes, whoosh, transition state, products, intermediate, all that good stuff, wavy stuff. All right, so go ahead and make that. Endothermic, exothermic, exothermic, exothermic. You don't really need to know why that is. Just understand that the first step for bromination is going to be endothermic, and both steps in chlorination is exothermic. Oh, and then this is exothermic as well. All right. If you really want a reason to remember it by, just know that the formation of the HBr bond is worse than the breaking of the carbon-hydrogen bond. So it wasn't quite worth it to break the carbon-hydrogen bond to make the HBr bond, because this bond's not as stable as that bond. But it could still potentially happen, and if it does, then you can proceed to your next step, and then the next step is favorable, so the reaction can occur forward. All right, extra information, if you didn't get that, don't worry. All right, so yeah, jump out the camera, go make your energy diagram here and here, and then we'll regroup in a few seconds. All right, hit pause. All right, welcome back. I know it's a big mess over here, but did you guys get this energy diagram and this energy diagram? Well, first of all, ignore this stuff, ignore that stuff that doesn't matter right now, ignore this stuff, ignore that. The main thing that you have to understand is this graph and this graph right here. So first off, x-axis is the reaction progress. So this is the beginning of the reaction. This is the end of the reaction. What reaction am I talking about? That one and this one. Okay. Y-axis is delta H or delta G. Doesn't really matter which one you think about. It just means energy. Lower means lower energy, more stable. Higher means higher energy, less stable. Okay. So yeah, hopefully you got this. In bromination, oh yeah, I should have said this. Both of these are the energy diagram for after initiation has already occurred. So that's why here's my starting material. I already have I have the starting alkane. I have the Br radical because initiation has already occurred. And I have a Br-Br that I'm going to use in the reaction. Okay? And then in the first step, it's going to be propagation 1. So if we analyze this top pathway, we form the primary radical because this bromine radical snatched the H. That's why it's HBr. And then the Br-Br hasn't participated in the reaction yet. Okay? All right, and then following it, what's the next step? Radical, homewrecker, breaks up the happy couple, Br-Br. And there you go. Boom, products. So that's how you kind of read this energy diagram, okay? So take a second, make sure you fully understand both diagrams. As you can see, it's kind of different. In bromination, you have an endothermic step for both of your paths, whether you're creating the tertiary radical or the primary radical. They're both endothermic, okay, like I said earlier, and then they're both exothermic to your products. And then for chlorination, you are both exothermic and then exothermic again to your products. All right, so the explanation you probably got from your professors at this point is that based on these energy diagrams and based on Hammond's postulate, which says that if a reaction is, one more thing, you only need to focus on the first step of the reaction to fully understand it, so propagation 1. So yeah, your professors would say, according to Hammond's postulate, if a reaction is endothermic, the transition states, which are these bumps right here, it would resemble the products more. And the opposite, if a reaction is exothermic, the first step, then the transition state will represent the starting material more. And then I sat in a few lectures, and that's kind of like where they left it, and they didn't explain any more, and it didn't really make that much sense to me because how does that explain the selectivity? And how can you just leave it right there, right? So there's a little bit more to it that they should have said if you don't get it. If you don't get it right now, that's good. You shouldn't get it. The explanation isn't complete. To take it a step further, what you should really consider is that for endothermic reaction, the transition states, they resemble the final products because they're at the end of the first step. Your reaction is happening, and then it's about to get to the product of the first step, which is your intermediate. And right before you get to the product, that's your transition state, that hump. So of course your transition state is going to resemble your product. You're like 99% of the way done with your first step of your reaction. So that's kind of what Hammond's postulate means. And for exothermic reaction, your reaction is just starting. when it gets to the transition state. You put in a little bit of energy and boom, you're in the transition state where bonds are breaking and half forming. And then you have to travel all the way down to get to your products. So that's why Hammond's postulate works. Your transition state is literally like 2 seconds after your reaction starts. And then for exothermic reactions. And then your transition state's like 5 hours after your reaction has already occurred. And you're like 2 seconds from getting to your product. Okay? But then there's still more though. Hold on. Okay, so now let me tell you how I taught my students before I fully understood it, and I'll tell you the real explanation, okay? Before, I would just explain to my student, bromination is selective because the first step is endothermic. So if you're climbing up a hill, then you might as well climb the lower hill. Why would you want to climb a higher hill if you can just climb this lower hill and get to a more stable product? Why would you ever go to the higher hill to create a more unstable intermediate to get to a more unstable product? It doesn't make sense at all. And then chlorination is exo. So if you're going downhill, just go downhill. It doesn't matter which stop you go at, because eventually you're going to end up more stable than you started. Okay, so that works, but now that doesn't work if your professor asks you to explain why these two reactions are selective on your exam. Or it's also helpful to just fully understand it. It's only going to take a few more minutes, and bear with me. And there's also some more cool stuff later with the calculations, so don't leave yet. Real quickly, to take it a step further, Hammond's postulate is useful because what it means is that, well, one thing you should notice, the difference in energy between the two transition states to get to your products for the first step in bromination. It's huge, right? Well, not huge, but it's huge when you compare it to the little tiny itsy-bitsy difference in activation transition state energy between the two transition states for an exothermic reaction like chlorination's first step, right? Is that kind of weird? Well, why is that? And this is where Hammond's postulate is useful. Well, turns out that if you want to look at the transition state stability, you just look at the starting material for chlorination. And for bromination, you just look at the products. So if we go over here to bromination, actually, no, I think we should start with chlorination. So chlorination, first step. If you look at these two, right? This is the starting material. If you block everything out, just look over here. Just this. Which one's more stable? Are you kind of confused? Because you should be. It's a trick question. They're the same starting material. There's no difference in stability or energy, right? It's the same starting material. So because it's the same starting material, the transition states aren't going to have that big of energy difference. Why would they? It's the same thing. Now, to complete the explanation, I'll complete it later. But if you look at bromination, Hammond's postulate says the transition state looks like the products. So we look at our products of propagation 1, so right here, ignore everything else, block everything out, these two. You have a tertiary radical here that's being stabilized by 3 carbons next door, all sending in their electrons, making it seem like you don't have a radical, but rather a lone pair. The concept is hyperconjugation. There's a video in my Orgo 1 playlist if you don't fully get that. But yeah, these 3 carbons are stabilizing this radical versus this is a primary radical, way less stable. Hopefully you heard that in class. So that's why first of all it's at a, sorry, wait, this one's up here. Yeah, that's why it's at higher energy and less stable than this one. And because the two products are so different energy, the transition states are so different energy, and they have a huge energy gap between them. And that's why bromination is so damn selective, okay? And we're not done yet, because you should see how the transition state actually looks like. So for chlorination, the reaction has just begun, right? So your transition state will look like this. This bond has just started to form for the primary position and the tertiary position. The bond has just started to form. And this bond, it's just started to break. So I'm going to do this. Okay. See how that bond is just starting to break? Well, that's still basically your starting material. There's no difference. It's just that you're starting to get a primary radical and you're starting to get a tertiary radical. So there's going to be a little teeny bit of more stableness in this one, in this transition state, than that transition state, okay? And if we go over to bromination, the reaction is 99% complete, or the first step, once again. I'm not talking about the entire reaction. So this bond is basically almost fully formed. I should have did this, actually. Yeah, the bond is almost fully formed, and this bond is almost completely destroyed. So yeah, there's like a teeny tiny bit of that bond left. So these two are the two transition states. The tertiary one should be here at that bump, and the primary one at that bump. So as you can see, that's why the transition states, to analyze the stabilities or the energy levels, you just look at the products. All right? Anyways, I thought this was really, really cool, and I was like mind blown when I finally got it. But yeah, and then to finish this video, because of this concept right here, scientists have figured out the reactivities at each site, the primary carbon, secondary carbon, and tertiary carbon for chlorination and bromination. So for example, I'll show you how that comes in handy, and that's how we actually calculate these percentages. But the primary site, so these primary carbons, they are 80 times less reactive than a secondary carbon that has a hydrogen, of course. We don't have that here, so let's jump to the tertiary carbon. The tertiary position is 1,640 times more likely to react than a primary hydrogen. Okay, all right. And then for chlorination, because energy gap isn't that big, well, it only has a 1 to 4 to 5 ratio. Okay, so now let's do a little bit math real quickly. So if we analyze this molecule here, this molecule has how many primary hydrogens? You should get 9, 3, 6, 9. And it's 9 because those 3 primary hydrogens will give us the same product. They would all give us this product here, because if you add a chlorine here, it's the same thing. You just rotate the molecule and you get this. Okay? So 9 primary hydrogens multiplied by the 1 reactivity at the primary site gives you 9. Okay? Then let's do the tertiary spot, 5. Well, there's 1 hydrogen, so 1 tertiary hydrogen times 9 reactivity gives you, sorry, no, not 9, times 5 reactivity gives you 5. Okay? And then 5 is for the tertiary, so we have a 5 to 9 ratio. And that's pretty close to 37% to 63%. You can test it on your calculator, actually. You can add up 5 and 9 to give you 14, and then divide 5 by 14, and you'll get 37%. Okay, now let's do this one. This one's gonna be cool, because we have 9, marker's dying on me, 9 primary hydrogens times 1 reactivity for the primary positions equals 9, same thing, but then we'll have 1 tertiary hydrogen times 1,640 reactivity to give us 1,640, and then you have a 9 to, actually let's flip this. Wait, 5 to 9, tertiary, wait, yeah, tertiary, okay, we can do it this way. 1640 to 1. That's gonna be the rate, oh, so no, geez, it's a long video. So 1640 to 9, that will give you 99% to barely 1%, okay? So actually, yeah, it's not approximately. I said approximately to simplify things, but it's actually way more than 99% and way less than 1%, okay? As we can see from these ratios. So that's the complete picture, and that's the complete story for why bromination is selective and chlorination is not selective. I hope you guys found that as cool as I did. Thanks for watching and making it here. I'll probably have some bloops at the end of this video, but thanks for watching. If you like this, let your friends know. Like this video down there. Get subscribed if you want to get notified when I make new videos like these. All right. And yeah, if you have any questions, put them in the comments. Let me know. Let me know what worked in this video, what didn't work so well. I'm always trying to improve. Okay? All right. I'll see you guys in another video then. Okay? Bye.